Not sure. So anyway, I'll just not sure why it's not coming presentation mode. So I hope this
No problem, sir. It is okay.
Fine. This is visible, right?
Yes, sir.
Okay. So very good morning to all the participants. So I'll talk about inertia in general, the concept of inertia, why inertia is very important and has become more relevant in renewable energy integrated systems. And when we talk of microgrids, it becomes of relatively of more concern because of the smaller size of the system if it is an AC microgrid. So please keep in mind we are talking of an AC system, small AC system, which can be a microgrid or a small islanded system. And in general, the concept will be, or the understanding will be applicable to the larger power systems as well. So I think this concept of microgrid and all that you would have already covered through various lectures. So I'm not going into that. What I am trying to point out here is that even in microgrid, one of the main focus is that it is distributed generated based, means more renewable energy based system, and therefore the number of synchronous generators or conventional or diesel generator, you can say, that are going to be in the microgrid system is going to be relatively less. So it is going to be primarily dominated by these what we call nowadays IBRs, inverter based resources, which can be wind generator, which can be solar PV system or battery energy storage system, basically a source interfaced through an inverter. So now when you have a source interfaced through inverter and the system is dominated by such sources, IBRs, then the question comes about the frequency. Frequency of or frequency control of the conventional systems has been well understood, well applied. The procedure, the concept, the operational procedure of controlling the frequency in conventional systems has been well adopted, well accepted, and well matured. However, this dynamics of this paradigm shift from conventional generators to IBRs is changing that basic structure of the operation of the grid or operation of the parallel sources in AC system. If it is an synchronized AC system, and of course these inverter-based source resources will be integrated through these inverters, and they will be synchronized with the grid through PLL or if it's grid forming converter without PLL. Now, the issue with this is, for example, different countries have different targets. We have now 500 gigawatt by 2030 in India. And if you talk of microgrids, you will have higher penetration of renewables. Or you can think of, if you look it from the grid perspective, even if you look at the state level grids, for example, let us say Tamil Nadu, Karnataka, they are smaller, relatively smaller grids, and they will be experiencing they are already experiencing a significant penetration of renewables. And apart from the advantages, obvious advantages that these renewables bring into the system, they bring several technical challenges. And one of the technical challenges is this inertia, diminishing inertia. This again, I'll not focus on this. So this is similar, context setting this slide, that renewable energy is being integrated more and more in the world, and then India is actually following the same trend. So without going into that statistics, what I want to point out here is that by introducing these inverter based resources, what is happening is they result into the displacement of conventional sources. If there are already conventional sources in the system, in the microgrid system, for example. Now, when you increase the number of renewable sources into it, what you will end up doing is you will either displace the conventional sources in microgrid DGs. In the main grid is going to be synchronous generators. You are going to displace those sources either temporarily or permanently. When I say temporarily means the source is still there, the diesel generator or synchronous generator is still there in the system, but because you have a decent amount of renewable, you will be dispatching the renewable. You'll be tapping in the generation from renewable. So what does that result into? You will not connect or you will not commit the conventional source. And these conventional sources have been providing this inertia in the system. And this inertia is the beauty of these conventional generators was that, or is that, they have inherent capability to support the grid, be it frequency or voltage. When it comes to frequency stability, since those who are familiar with the synchronous machine operation, the rotation, the speed of the machine or the poles of the machine are locked with the rotating field of the stator. When I say rotating field on the stator, it means the rotor poles are locked with the magnetic poles of the stator, or in other words, rotor is locked to the speed of the grid frequency. Is locked to the frequency of the grid. The moment there would be any disturbance in the frequency or disturbance in frequency is because of the generation load imbalance. The moment that disturbance appears in the grid in conventional systems, because of this magnetic locking, the speed of the machine will decrease. And as a result, it will release instantly some additional power to the grid from the rotating mass of the machine. This happens inherently, but more important, instantly. It is just at the onset of the disturbance, it immediately releases additional energy to the grid. We'll understand why it is important in slides, few slides down. So here, I am assuming that you in this course you would not have got much introduction into the technology side of these renewables. So I'll just briefly touch upon them. Wind and solar PV primarily. See, wind, if you look at the wind generation technology, it has four major, not major, it has four types commercially available, four types of generators. One is type 1 wind turbine generator, where you have a squirrel cage induction machine connecting this blade and the shaft through a gearbox. Gearbox is very important here in the wind because wind speed is low and you have 10 to 20 rpm that will be here on the blade side of the shaft. But this squirrel cage induction machine will be rated at around 1500 rpm. So you need this gearbox of a ratio of around 100, the 1:100, so that it boosts the speed of this rotational speed to the rated speed of the machine. So therefore, gearbox is important. Now this machine is directly, the stator is directly connected to the grid in this first type of the machine, which is also known as Danish concept wind turbine generator. Because if you look at the history of the wind, Denmark and Germany are the pioneers in the wind generation technology. It primarily started from there. Solar was not even in much focus then. We are talking of 1980s, post 1970s oil crisis. It was wind. Solar started coming, showing its presence more from 2000 onwards, whereas wind started actually 1980s onwards. That's why as of today also, wind technology is a mature technology, while a solar PV is not a mature technology. It's not as mature as wind. Wind is well established mature technology. We are yet to reach to that level of the maturity when it comes to solar PV technology. Solar PV started, the focus on solar PV started in 2000 onwards, and primarily because of the falling prices from 2010 onwards, there has been a rapid increase in integration of solar PV. Till then, it has been primarily wind. Though, as of now, solar is now almost started overtaking the wind installed capacity at the global level, but it has been wind predominantly earlier. So this first type of wind turbine generator, which is based on squirrel cage induction generator, machine-based wind turbine generator, or Danish concept of wind turbine generator, was the first of its series in modern wind turbine generators. Of course, we have wind. The history of taking power or extracting power from the wind is very, very old. Windmills have been there for centuries old concept. So what we are talking here is about modern wind turbine technology. And then it had some limitations. So the stator is directly connected to the grid. So you can see stator frequency is the grid frequency here. So rotating magnetic field will rotate at the grid frequency, and rotor will rotate at a slip frequency. In this case, there were some issues that you could not actually control the speed of the machine. If you could not control the speed of the machine, you cannot extract more power or maximum power from this. And there were several issues also. We'll not go into that. So then in this series, next to type 1, it was type 2 wind turbine generator. The only difference between type 1 and type 2 is this machine, electrical machine, is wound rotor induction generator or slip ring induction generator. So that you have an access to the rotor circuit. By that, you can control the external resistance. So you can control the torque slip characteristics of the machine. And that allows you to control the speed of the machine. And as such, by controlling the speed of the machine, you could actually increase the operating range of the machine, and you could have limited maximum power point operation within plus minus 10% speed of the machine. This did not serve much purpose. Of course, there were other issues, grid code regulations, all that. And then that resulted into the type 3 wind turbine generator, which is commonly known as DFIG, doubly fed induction generator. So in this case, what the machine looks like is, you again have a gearbox and blades, but rotor circuit is connected through back-to-back converter to the grid. Of course, this figure is not technically very correct. Normally, this transformer is a 3-winding transformer, and this rotor is connected to one of the primary windings. So you have this rotor circuit connect through back-to-back converter, and stator circuit directly connect to the transformer or the grid, you can say. By having this back-to-back converter, particularly this rotor side converter, you have a control over the frequency and magnitude of the current that you will feed into the rotor of this machine. That allows you to control the speed of the machine and also P and Q exchanged with the grid. So it gave more control flexibility, both in terms of active power, reactive power, and the speed of the machine. And that allowed this maximum power point operation. And this is allowing 30% variation around the nominal speed of the machine. You can operate it at nominal speed and plus minus 30% range of that plus minus nominal speed. That gives you a good space of control flexibility, and you can extract maximum power, and you can support the grid if required. And then in the series, which is the latest one, is this type 4 wind turbine generator. So here the rating of this back-to-back converter, each back-to-back converter is 30% of the rating of the machine of this wind turbine generator. Here you are transferring entire power to this back-to-back converter. So the rating of this converter has to be at least equal to the rating of the wind turbine generator. Here it can be permanent magnet synchronous generator, or it can be spiral cage induction generator, it can be synchronous generator, it can be other generators. And you do not necessarily need the gearbox here, because the stator of the machine is connected to back-to-back converter. This type 1 and type 2 wind turbine generators are obsolete technology. They are no more manufactured for some reasons. We'll not go into that discussion. They are no more being manufactured currently. It is primarily this type 3 and type 4 which are being manufactured and installed in the field. So what I want to put out here is the majority of wind turbine generators that you will have in the system is going to be type 3 and type 4 together. And all the new wind turbine power plants, wind power plants, is going to have these type 3 and type 4. Type 3 or type 4 are potentially combination of these types in the system. So what is happening with this type 4? It is clear that it is not going to provide the inertia to the grid. It cannot provide inertia to the system. So the reason being is it's not synchronized to the grid. If this, you see that type 3, no, it's not magnetically, machine is not magnetically locked to the grid. If you see type 3, you may still say that the stator is still connected directly to the grid, though the rotor is connected through the back-to-back converter. But what the issue here is that since you have a control here, because of that control that you have in the system, this control will not allow change in the speed of the machine, and that does not allow the inertial contribution to the grid. So therefore, these wind turbine generators inherently cannot provide inertia to the system. That was the point, the message that I wanted to put across. Same is the case with solar PV. They will be connected through these inverters, right? You have different topologies, central topology, string topology, multi-string topology, and modular integrated topology. But all are connected to the grid through inverter at the end. And inverter decouples the frequency of the grid and the source on the other side. And because of the end, the other point is they are, there is no rotating part in the solar PV system. So as such, there is no inherent inertia available in these solar PV systems. Even though in wind you have a rotating mass, but because of the decoupling provided by these solar, inverters, you are not able to provide the inertia to the grid. And this inertia, lack of inertia contribution from these renewable sources, poses a challenge to the stable operation of the grid. See, one of the fundamental requirement of operating AC grid is that there should be instantaneous balance between generation and load. When I say instantaneous, it literally means at each and every instant, not at sub-second level also. At each and every instant, there must be a balance between generation and load. If that is not met, the grid can collapse. The frequency will drop and the grid can collapse. So fundamental requirement of operating this AC system, AC microgrid or the larger AC system is that you should be having instantaneous balance between generation and load. And if that is not there, the grid is going to collapse. Now the point is, the problem is, let us say you have a sudden generation loss or load outage, or connection of a larger load to the grid. Conventional generators cannot instantly change their power output. Those who are familiar with the operation of the conventional generators would appreciate that the change in power output of the conventional generators is through the governor control. And if the generator, synchronous generator, is generating a power, so this is power and this is time, and there is a sudden change in the generation and load balance, means the either generation outage is there due to some fault or due to some event, or there is a load outage, or there is a load connection, large load connection. What will happen if this is the instant of the disturbance? The power output from the governor will start increasing only after delay of 2 to 3 seconds. It will start increasing after delay of 2 to 3 seconds, because governor needs to detect the change in frequency of the grid or change in the speed of the machine, right? So frequency of the grid and speed of the machine are coupled, they are locked with each other. So whether you talk of the frequency of the grid or the speed of the machine, it is indirectly same thing. So during these 2-3 seconds, we are violating that basic fundamental principle of generation load imbalance, where I said at each and every instant there must be a balance between generation and load. And because of sudden change in the generation load balance, and because the governor of the generator, conventional generator, cannot change its power instantly, you are vulnerable to the grid outage. And this is where the inertia comes into picture. As I said, inertia is an inherent and instantaneous support that conventional generators have been providing across the system over the past history of the electrical grid. So what happens is, when you have here a generation outage, so let us take an example, a generation outage. What will happen? Let us say X megawatt of generation is lost. At this, before the generation outage, it was operating at nominal frequency, that is, let us say 50 hertz if we are talking of Indian and European system. So it is 50 hertz. It is operating at 50 hertz, and the generator that is connected to the grid is having stored energy 1/2 J omega synchronous scat. 1/2 J omega scat. J is the moment of inertia. Omega is the rotational speed of the machine, which is synchronous speed because the machine is operating at synchronous speed. So as I said, there is Pn by 120 is equal to F. If F is the grid frequency at synchronous frequency, N is going to be Ns or omega S, rotational speed. What will happen if there is a generation outage? Load is now more than the generation. Part of generation is lost. Load remains intact. So therefore, because of load being more than generation, what will happen? See, at the end of the day, you have to see this whole AC system through a basic electrical circuit. When you increase the current from the load, it has to come from the source side, voltage source side. That's going to be generator. So what will happen is that additional load that was supplied by this generator, which is lost now from the grid, will be supplied by the nearest generators primarily. means the nearest generators will start getting overloaded. And this balance between mechanical torque and electrical torque, which was earlier there during normal operation, gets disturbed. So electrical torque becomes more than mechanical torque. Because mechanical torque cannot change instantly, electrical can change instantly. So because of this change in electrical torque, which is going to be now more than mechanical torque in a synchronous generator, what will happen is the synchronous generator will slow down. The speed of the machine will start going down. If the speed of the machine starts going down, what will happen? The frequency of the system starts going down. When the machine starts slowing down, let us say it reaches from N1, which was Ns, to N2 now. Its speed decreases to N2. What is the energy stored at N2 or omega 2? It is going to be 1 by 2 j omega 2 square. Now, if you see that in this process of slowing down the speed of the machine, slowing down the speed of the machine, there is a change in energy stored by the machine that is now E1 minus E2. That's going to be 1 by 2 j omega s synchronous square minus omega 2 square. There is a loss of energy stored in the machine in the process of speed slowing down. And this energy goes into the grid. It is released to the grid inherently without any control. You do not have any control to execute this release of additional energy to the grid. This happens because of the natural laws of the electricity and because of the magnetic locking between the rotor of the synchronous machine and the grid frequency. So therefore, it is this inertia, rotational energy which is stored in the machine and gets released instantly to the grid. It is this support, instant power support, that is provided to the grid by this synchronous machine is known as inertia. And this is what precisely saves us from losing the integrity and stability of the grid at the start of the disturbance. So this inertial response from the synchronous machine comes into picture. It supports the grid initially for first few seconds. As I said, after 3-4 seconds, the governor starts reacting, and then the input power increases to the synchronous machine and the output power accordingly increases. So as I was showing here, what will happen now in this case, this was the governor response. But the inertia will start increasing here itself because it's instantaneous. Inertia will start increasing here. And the total power output from the machine will start increasing here itself. And of course, if you have, depending on where your governor settles down after this disturbance, you will have the power output here accordingly. And inertia will settle down again, back, inertial response. So inertial response is going to be very fast, but it's going to be for shorter duration. So it is this inertia which has been saving the conventional system from, because this is what is making sure that there is instantaneous balance between generation and load in the grid at each and every instant. Otherwise, you cannot, there is no technology in the world that can bring the additional generation as fast as this inertial response is there. Now it is when you are integrating these renewables into the grid, you are displacing the conventional sources, you are diminishing this inertial power in the grid. Or if you talk of, let us say, a new microgrid, where you are dominating primarily with the renewable sources, you already have very low inertia to start with. And now since you are in a dearth of this inertia, you have a vulnerability of this frequency falling, straight away to the values which are unacceptable, where the protection of the grid has to get activated and the system blackout will take place. As you see in this plot, for the same system, what we did is, it is the same system, but we increased the renewable energy penetration. Same system, same generation outage. This is the conventional system. This black response, frequency response, the conventional system. But when you increase the penetration from the conventional system to this, higher penetration, which in this case is 1.5 gigawatt seconds, means this is the kinetic energy, rotational energy in the system. It has decreased from 3 gigawatt seconds to 1.5 gigawatt seconds because of renewable energy integration. The frequency falls down further. If you further increase the renewable energy penetration, the frequency falls down further for the very same generation outage in the very same system. This is all because of diminishing inertia, because you do not have a sufficient inertia released at the beginning, and this is frequency here, of course, and you do not have inertial support, insufficient inertial support in the beginning, and therefore you are vulnerable to the frequency stability issue. That is the essence of this inertia in the operation of the grid. It is well accepted fact that lack of inertia is potentially going to result in the issues in the grid. This is one of the study conducted on Irish power system, and you can see for compared to 2010 system, the system is insecure, is potentially insecure for more than around 28% of the time of the year because of lack of sufficient inertia. And why I took Ireland here? Ireland is a small islanded system, and of course it has HVDC connection, but if you see the synchronous, it's a small islanded synchronous system, and that has a lot of similarity with the microgrid. Microgrid is going to be smaller system and much smaller system, and therefore the vulnerability of a microgrid is going to be more to the frequency instability because of lack of inertia. This is an ERCOT system in Texas, which shows that inertia of the grid decreasing with the increase in penetration, renewable energy penetration. It is decreasing with the increase. The field data, where data collected from 2015 to 17, with the increase in penetration, the inertia of the grid is decreasing, and that is posing an issue to the grid operator. Now, solar PV inverters and wind turbine generators, as I mentioned earlier, inherently cannot provide inertial support to the grid because they are not having that magnetic coupling that this conventional generator had with the magnetic poles of the stator. You do not have this coupling between the poles of the rotor and the poles of the stator in renewable energy generators. So since you do not have this magnetic locking, there is a decouple between frequency of the grid and the machine or the solar PV system or battery energy storage system on the DC side. So what you have is, you have this inverter and you have here DC link, and you have here the source, whatever, now wind or solar or battery. The frequency of the grid can fall here. This system, energy system, or energy source on the DC side is not going to detect the frequency decrease here unless it is indirectly being told that there is a frequency decrease in the main grid. So therefore, it is a kind of blind about what is happening on the grid side. The energy source on the DC side of this inverter is a kind of entirely unaware of what is happening on the AC side of the grid. So therefore, inherently, it cannot detect the frequency decrease or frequency rise on the grid side. Therefore, inherently, it is not going to, and it's not coupled magnetically locked the way conventional generators is. It's not going to, provide this inertial support. So there is no inherent inertial support from this renewable energy. Now the question is how to address this diminishing inertia in this renewable energy dominated system, particularly smaller system we are talking of, microgrid, or relatively larger systems, but islanded systems. So what is going to happen here is we have to see what are the potential source of inertia. What over the period of this development of this technology, solar PV and wind, particularly wind, again I'll start with wind because that technology was earlier than the solar PV technology, if you see from the growth and maturity perspective. So the idea was that in wind turbine there is already a machine, rotating machine. There is already a kinetic energy, rotating energy stored in that rotating machine. Why can't we exploit that rotational energy to support the grid, similar to how the inertia in the conventional generator supports the grid? So therefore, the concept of this, what we call as emulated inertial response, sometimes synthetic inertial response, sometimes virtual inertia, various names. We can later on discuss that. What does the different terminology mean? So basically, it is emulated inertial response, similar to the synchronous machines, that is from wind power plants can be extracted, and to some extent it can address the issue of diminishing inertia. Similarly, this EIR, emulated inertial response, or virtual inertia from solar PV plants, we'll talk about it. Solar PV plants can also provide the inertial response, both with storage and without storage. Emulated inertial response from battery energy storage system or energy storage system is another possibility, EVs and others. But let us restrict our today's discussion to wind and solar PV system, or potentially battery also. So what is this, as I mentioned, what is emulated inertia? What is this virtual inertia? It is a kind of forced fast response on the inverter interfaced machine, inverter interfaced generation source, to provide fast active power response to the grid. Similar, but it is not going to be identical. That's why I'm using the word similar to the synchronous machines. Means if a wind or solar PV plant is generating power, here, like this. If our disturbances are happening at this point, this is time, ideally, if there is no inertial response from the solar PV or wind, the power output from the solar PV and wind will remain unchanged, irrespective of whatever the frequency is happening or the disturbance is happening on the grid side. But if you employ an additional control to this wind or solar PV system, such that it immediately informs the grid, the control of the machine, of the solar PV or wind system, that there is a decrease in the frequency of the grid, you need to increase the power output, it can increase the power output. It can increase the power output. So it's going to be somewhat like this. So it is going to increase instantly, or you can say quickly, it's going to increase the power output. If you employ an external controller, what we call as inertial controller, that pass on the frequency information from the grid side to the controller side, and it forces the energy system or energy source, be it wind, solar, battery, to increase the power output. That is how it works. And before going into further detail is how it works, we need to little bit brush up, if you are already familiar with the classification of converters that are interfacing these energy sources, renewable energy sources. So there are primarily these grid feeding power converters or grid following, what we call as grid following power converters, are the predominant converters that are available in the market that interface this renewable energy source with the grid. The grid following, grid feeding, means it follows the voltage of the grid. So they are basically current source converters. They just have a control over the current. They are just following the grid voltage. The other category is grid forming converter, which forms the grid which has the control over the voltage at its terminal and the angle, voltage angle that it forms at the terminal of the inverter. And then there is a third category, is grid supporting power converter. Now this can be both of them, grid forming or grid following with grid support capability. And one grid support capability is this inertial support. Means you make them to support the grid through an additional supplementary control. So you have these three types: grid forming, grid following, and grid support power converters. Okay. Now let us try to understand how the supplementary control can help us to extract the power from the wind. Means instant power, that is inertial power. What is happening is you have this frequency measured at the grid side of the machine. This is DFIG, that type 3 wind turbine generator. This is the supplementary controller that I was talking about, inertial controller. You measure the frequency, you pass it on through the differentiation block so that you get dF by dt. Now in swimming equation, you have this dF by dt, which is normally known as Rockoff, rate of change of frequency. So you have dF by dt signal and you have delta F signal going to this controller. And based on that, you send a signal to the controller and you give it a signal that, let us say, before the disturbance, when frequency was nominal, meaning this was 0, delta F and this was 0, dF by dt will be 0 if frequency is nominal or steady state, and delta F is going to be 0. So you have 0 signal from the inertial controller. But if there is a disturbance in the frequency, now F is going to be less than F steady state or nominal value. So you have dF by dt non-zero, you have delta F non-zero. And that gives this signal as a non-zero. Before the disturbance, since these were 0, the power command for power reference that was going to this rotor side converter was, let us say, generally maximum power point reference. But because of the disturbance, this power reference that goes to this rotor side converter is now Pref plus delta P, and delta P is additional command from this inertial controller. Now what is the output power that forces this generator to generate P MPP plus delta P? It is forcing it to generate power more than MPP. Now you are not able to have additional power from the aerodynamics power, that is the wind, because you are already operating it at maximum power point. So what will happen in this case? This delta P additional power will be extracted from the rotational energy of this machine, and that will, so there is this pitch control with the blades and all that comes into picture in some cases, but primarily it decreases the speed of this machine. So you can see here what is happening. This is the electrical power output of the machine. Because of the disturbance in the frequency of the grid, that is change in the frequency of the grid, this delta P, as I was mentioning, it increases. But what you need to keep in mind is the mechanical power generated from this turbine, which is torque into omega, is going to decrease. This is mechanical power, right? Before the disturbance, it was generating torque into omega that was equal to MPP. But now, because you give a delta P signal to the grid, to this controller, it started extracting the power from same concept. It releases additional power from this 1/2 j omega square. And because of that, the speed of the machine goes down. Since the speed of the machine goes down, the mechanical power generated by this machine decreases. But the summation of this mechanical power and delta P that is coming from this rotational energy is still higher than this power, earlier power, pre-disturbance power. So the power seen by the grid is going to now increase, even though mechanical power further decreases. And after some time, when the frequency starts coming back, this signal goes to zero or signal is cut. And then what is happening is, now the speed of the machine has decreased. It has to recover back to the nominal or pre-disturbance speed. It starts increasing its power output, mechanical power output, because of the increase in speed. And then it reaches steady state power. So initially it increases the power output, but later on it takes additional power to gain its speed back to the nominal speed or pre-disturbance speed of the machine. And if you look, this is known as power speed plot here, this is the maximum power point curve. And let us say it was operating at point A, and because of this inertial controller and disturbance in the frequency, it increases the power output to B suddenly. And it continues for some time. Why it is going reverse? Because the speed is decreasing for the reason I mentioned. It continues for some time till C, and then because of the controller, the speed hits its limit, which is normally 0.7 per unit, the machine now decreases its electrical power because it has to gain its speed. So net power after this inertial power release is going to be less from the wind turbine, and that is how it works in wind turbine. But it has to maintain this energy balance. Whatever additional power it generated has to be taken back so that its speed regains. This is not the case in synchronous machinery because the governor comes into picture. Additional power is fed from the backside mechanical side, which does not happen here, and therefore here in wind turbine generator, after providing the inertial response, it needs to take back that energy to gain its speed to its pre-disturbance value. That is how wind turbines can potentially, and do in some parts of the world, participate in inertial response. And this is one of the study we did here at IIT Bombay, which shows that these are the different frequency curves, and this shows the penetration versus frequency nadir, that's the worst frequency. And if you see this inertial puller droop control, which I was explaining in the previous slide, you have the best nadir in all the cases. This is the base case without any inertial control. This is with only df by dt loop. This is with both df by dt plus delta f loop of the inertial controller, and you are able to maintain the frequency nadir at a lower level, or you can say improved level, compared to if you would not have inertial response from the this wind turbine generators. Yeah, so inertial support from solar PV plants. Let us try to understand now how solar PV power plants can potentially support the inertial power in the grid. We all know that this is the, let us say, a solar PV curve of the solar PV system, and normally what will happen, it will operate at MPP, maximum power point. If the solar PV system is operating at MPP, This is inverter. This is grid. If it is operating at MPP, means it doesn't have rotational mass is anyway absent. The stationary devices, it doesn't have any additional energy that it can provide the inertial power to the grid. So therefore, if the solar PV system is operating at MPP, it cannot provide inertial support to the grid. However, if you want to have an inertial power from the grid, from solar PV system, pure solar PV system without any storage, then what you need to do is you need to operate it at suboptimal point. Let us say you have now A and B. You have two possible operating points of the solar PV system, A and B. For the same delta P, for same curtailed power or deloaded point, you have two operating points. One is A and B. Of course, I did not draw it so precisely. Normally, it will be like this, right? This slope is going to be faster. The right side slope is going to be faster than the left side of the left side slope. So what will happen is you have two possible operating points, A and B. This is power, this is voltage. Now the question is, okay, before going to that, now if you operate it at suboptimal point, what will happen is you have a margin of delta P with you. And the control of the solar PV system is very fast. It's a power electronic control. So you can quickly, very quickly bring this operating point from A to P, let us say C, or B to C, depending on where you are operating it. You can quickly bring it to the MPP point. And that what will happen if the solar PV system was generating power P and a disturbance, because it is having the margin of delta P, it can quickly increase the power and then it can stay there. So this is going to be inertial power. Solar PV plant without storage can provide inertial support as long as it is operating at suboptimal point. But now the question is, we have two potential operating points to operate this solar PV system at non-MPP point. There are pros and cons on both the sides. So where to operate? If you look at this side of the PV curve, the disadvantage or a limitation is that the response here, when you start increasing this, is going to be relatively sluggish because slope is slow. It is going to be relatively sluggish, and you will not have very fast increase in the output of the power if you are operating it at point A. But if you operate at point B, since the slope is faster, you can quickly come back to the maximum power point, and therefore you are going to have faster increase in the power output. But the limitation of operating it at this point is, is two. Let's say this is B dash and this is A dash. VA dash, VB dash. One is that you are operating it at over voltage, relatively on higher voltage. And that can potentially stress the electrical infrastructure of this, PV modules, DC link, capacitor, and others if you have. Potentially. That is one limitation. The other potential limitation is it is going to be more prone to open circuit operation, right? If you further do, it can actually result into open circuit operation of the solar PV system. That is another disadvantage here. Both the limitations are not there here on the left side of the operating point, because voltage is going to be on the lower side, so no voltage stress, and there is no chance of going to the open circuit operating point on when it is operated at A. But to be precise, depending on various design factors, you can potentially technically operate it on both sides and yet provide the inertial support. But for faster inertial support, you are going to have this B as a preferable point, operating point. And that's how you can provide inertial support from solar PV system. Okay, this is one of the field study, a demonstration study, where this 20 megawatt solar PV power plant was tested for this grid support, including frequency support. And it is 20 megawatt power plant. It has number of inverters connected to it, and the controller was designed such that there was a central controller which could send the command to each inverter in this solar PV plant. And you can see here the power output. This is the power output in kilowatt. It's a 20 megawatt plant, and what is happening here is this signal, you can see, is a frequency signal. Now, see, frequency signal cannot be triggered in the live system. So therefore, what they did is they sent a fictitious frequency signal to the controller. And that is this frequency signal, not the actual grid frequency signal. They sent a modulated frequency signal to the grid controller, means they decreased it from 60 hertz to 59 hertz by 1 hertz. And the plant started increasing the power almost immediately with some delay. I'll talk about this delay, where does it come from, and that it increases the power output, which is not a possibility in conventional generators. Now you see here, within 500 milliseconds, that is within 0.5 seconds, it actually reached to its value, target value. And as I said, in synchronous machines, had it not been for the synchronous inertia, governor control starts after 2-3 seconds responding, and then when it reaches to the target value is a different question. It is further with further delay. So what is happening here is it is reaching to its steady state value within 500 milliseconds. So this delay, initial delay, is potentially going to be there due to the measurement of the frequency signal, due to the processing of the signal, sending it to the controller, and that potential communication delay within the power plant. It's all that which ranges from 50 to around 50 milliseconds to 100 milliseconds in some cases. And so what does it mean? It is not exactly same instantaneous response from these inverter based sources when it comes to its comparison with the synchronous response. What I said, in synchronous response in synchronous generators, the inertia starts instantly. Here, even though it is very fast, there is still a delay of 50 to 100 milliseconds in particular grid following converters. Grid following converters are relatively faster, yet they cannot be considered as identical response as that of the synchronous inertia. I think in the interest of time, I was going to talk about estimation part also, estimation of inertia in microgrids. In the interest of time, I think I have to stop here. I hope that I was able to put across a message of this inertia and its impact on the operation of the microgrid in general, and also in the islanded system in particular. So, what are the potential sources of this inertia that could support the frequency of the grid? So therefore, I would stop here and leave it to the organizers, back to the organizers, and please let me know if there are any questions that would be there related to this topic. I'll be happy to take them.
Yes, participants, if you have any question, please very quickly you can throw some questions. Dr. Zakir has worked very extensively in the field of estimating and finding and significance of the inertia. It is maybe different names. It may be called as virtual, synthetic, or emulated one. And he has also suggested some very interesting remedies to address the low inertia system, like wind and PV especially. So if you have any relevant question, please quickly ask. He has rescheduled his thing particularly for this session. Yes, participants. Sir, you have already explained that thing, but I just want to ask you a question. Maybe I don't know whether it may be at the correct place at or not. So you have shown in solar photovoltaic as well as the wind system that the system may not be operating at MPPT point just to keep some safe margin. So it means that all the time we have to operate the system other than the MPP point at all the time, or when it is anticipated that it's going to change, it's going to have some change in the system, and then at that point we predict that and then we shift the operating point from the MPP to some other points.
See, for wind turbine generator, to provide inertial support, you do not necessarily need to operate it at deloaded point. You can operate it at MPP point, and since you have the rotational mass there, you have already stored kinetic energy. You are releasing the additional power from that stored kinetic energy. So you are not going to, you don't need to operate the wind turbine generator at non-MPP if you are participating in inertial support. So it's not necessarily for that, because you are providing the additional power from the rotational mass of the machine. But if it is a solar PV system alone without storage, then you have to, if you are planning to participate in the inertial support, you have to operate it at suboptimal point. You need to have a margin for that. Now the question can potentially arise is, one is what you pointed out: do we need to operate it throughout its operation at non-MPP point, or only in the anticipation of participating in inertia around that particular time? See, as of now, what some of the grid code regulations are mandating, for example, let us say in Canada, Hydro-Quebec, and some other parts, they mandate the control capability only. Means the power of solar PV or wind turbine generator should be capable of providing the inertial support. But they do not mandate them, force them to operate at non-MPP, because there is a revenue loss involved in that. So what you could think practically, there is a concept of ancillary service market, which those who are working power system should be familiar with. If inertia is being procured in the ancillary service market, then you have a market to go and participate in this and potentially earn the revenue. And if it does make economic sense to keep a margin for that, you will operate it at non-MPP. If it does not make economic sense, you will not operate your solar PV plant or particularly solar PV system we are talking here at MPP point. You will operate it always at MPP point. In addition to this, there is a concept of renewable energy curtailment. Sometimes because of various reasons, particularly grid stability reasons. For example, in Ireland, back in 2011, the maximum penetration of wind and solar power, that was restricted to 50%. You could not go beyond that because you have stability constraints. Now they had to curtail wind power primarily beyond 50%. So if your plant solar PV or wind is already being curtailed because of, let's say, other reasons, you already have to operate it at non-MPP. And you can think of participating in this inertial and frequency support if required by the grid operator. These are the potential operating conditions where you can operate in non-MPP point and participate in inertial and frequency support. Hope that answers your question.
Yes, sir. Yes, I got the answer. So one of the potential ways to handle this issue could be energy storage bagged system could also be suggested, I guess.
If
in case
the
of
solar
PV.
PV system is having energy storage, let's say battery energy storage,
Yes.
BESS, then of course you don't need to operate it at MPP. You can always provide inertial support from battery.
And it would be ready to supply as and when required, that initial support.
As and when required, yes.
So that helps in generating revenue as well as stabilizing the system also.
Yeah, as long as the storage is there, but you may not, most of the cases you are unlikely to have storage with the solar PV system.
So any question from participants? Sir, there is one question, if you can quickly answer. Is the inertia from the motor load can be counted for calculation of total inertia? In the chat box.
Yes, so this is a good question. See, inertia, we have been talking about inertia from generation side only. But there is a potential inertial support from the load side also. And this comes from particularly rotating machines, which involves primarily synchronous motors and induction motors as well. So synchronous motors will participate in the inertial support similar to what I explained the synchronous generator. But induction motors will also support the grid. See that when I was talking about inherent beauty of this synchronous machine, its conventional power system, it is this on load side also. When the frequency decreases, the load side, particularly motor side and be it induction and synchronous motor, their power also decreases normally, depending on which type of the induction motor you are talking about, considering their load characteristics. So they also participate in this inertial response or the frequency support response. So yes, load side contribute to the inertial response, and in some cases it has been reported that the percentage contribution of inertia from the load side can go as high as 20% of the total inertia contribution in the system. So load inertia definitely is a reasonable part of this, and particularly if you have rotating machines. Let us say we have air conditioning here in the country. We have industrial motors. We have other, domestic motors that we use for domestic application. Depending on that, the share of this motor load, which is directly connected to the grid. Again, I am not talking about the drivers. When it comes to drivers, they will not let that happen. This direct coupled, induction motor or synchronous motors will be anyway directly coupled. So hope that answers this load side contribution question.
Yes, that answers the question, sir. So any other question? Otherwise, we'll wind up this session. Okay, Dr. Zakir, it was very great to listening to you, and the session is very much useful, very much informative, and thank you very much for your time that you have spared from your busy schedule. I know that yesterday also you were so busy, and thanks for rescheduling your session today. So we are on entire team of this FDP. We are very much thankful to you, and we'll be in touch with you whenever we need your help, sir. Thank you very much, sir.
Thank you so much. Thanks a lot. Sorry that I did not have much time. This topic normally needs, will need 2-3 hours discussion. I try to, squeeze it within 1 hour. But I hope I was still able to put across some basic message.
Yes, sir. Yes, sir.
And it was a pleasure to, make this presentation here. Thank you so much.
Thank you very much, sir. Thank you very much. Thank you. Okay, participants, we'll start next session within 5 minutes. So please be online and don't leave the meeting. We'll start within 5 minutes.